Hello everyone, welcome back to the channel. In today's video, we're going to tackle one of the most frequently asked topics in Python interviews, recursion. Recursion is a powerful technique where a function calls itself to solve smaller instances of a problem. It's often used for problems like calculating factorials, solving the Fibonacci sequence, and traversing trees. We'll dive into some practical recursion questions you're likely to encounter in coding interviews and break them down step by step. Definition. Definition. Recursion in Python is a technique where a function calls itself to solve a problem. It's a way to take a complex problem and break it down into smaller, more manageable pieces. Each recursive call tackles a smaller version of the problem until it reaches something simple enough to solve directly. This is called the base case. Without a base case, the recursion would keep going and eventually lead to an infinite loop, so it's important to have a condition that tells the function when to stop. Recursion is super useful in situations like calculating factorials, working with Fibonacci numbers, or even navigating through tree-like structures. It's kind of like peeling off layers of a problem one layer at a time until you reach the core and can start putting the pieces back together. The syntax is straightforward. You define a function, check for the base case, and if it's not met, you call the function again with modified parameters. It's like having the function keep calling itself until the base case is satisfied, then it returns the result. Now that we've got a good understanding of what recursion is and its syntax, let's jump into some practical questions to see it in action. These examples will help solidify how recursion can solve complex problems by breaking them down into smaller steps. Let's get started with the first one. 1. Factorial of a number. Question: write a recursive function to find the factorial of a given number. The factorial function we're working with is a classic example of recursion, which is when a function calls itself to solve a smaller part of the same problem. Let's break it down simply. Factorial, denoted as n, is basically the product of all numbers from n down to 1. For example, 5 factorial of 5 is 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1 equal to 120. The function starts with the base case where it checks if n is 0 or 1. This is important because the factorial of 0 and 1 is always 1, and it gives the function a stopping point to avoid an infinite loop. So if n is either 0 or 1, the function simply returns 1. Now, for any other number greater than 1, the function enters its recursive case. Here's where things get interesting. It multiplies n by the result of calling factorial n1. This means it's continuously calling itself with a smaller value until it reaches that base case. For instance, when you call factorial 5, it calls factorial 4, which calls factorial 3, and so on until it hits factorial 1, which returns 1. Once the function reaches the base case, it begins to unwind, meaning each previous call gets its result and multiplies it by n. So factorial 2 becomes 2 multiplied by 1, factorial 3 becomes 3 multiplied by 2, and it keeps going until factorial 5 returns 5 multiplied by 24 equal to 120. And that's how we get the result. It's a neat and efficient way to break a big problem into smaller chunks, all while using the same function over and over again. 2. Fibonacci series. Question: write a recursive function to generate the nth Fibonacci number. The Fibonacci function is a great example of how recursion can be used to calculate the Fibonacci sequence, which is a series of numbers where each number is the sum of the two preceding ones. The sequence starts with 0 and 1. So, if you're calculating the sixth Fibonacci number, it looks something like this: 0, 1, 1, 2, 3, 5, 8, and the sixth number is 8. Here's how the function works. It starts with two base cases. If n is 0 or 1, it directly returns n. These base cases prevent the recursion from going on forever. For n equal to 0, it returns 0, and for n equal to 1, it returns 1, which are the first two Fibonacci numbers. For any number larger than 1, the function moves to the recursive case, where it calculates the Fibonacci number as the sum of the two previous Fibonacci number h. So when you call Fibonacci 6, the function breaks the problem down by calling Fibonacci 5 and Fibonacci 4. This pattern keeps going until the function reaches the base cases. For instance, Fibonacci 5 will call Fibonacci 4 and Fibonacci 3, and so on all the way down to Fibonacci 1 and Fibonacci 0, which return 1 and 0 respectively. Once the base cases return their values, the recursion starts to unwind, adding the results together step by step. For example, Fibonacci 2 returns 1 plus 0 equal to 1, Fibonacci 3 returns 1 plus 1 equal to 2, and so on until it works its way back up to Fibonacci 6, which gives us 8. This approach neatly divides the problem into smaller, manageable chunks until it reaches the simplest case, then adds everything up to get the final result. 3. Sum of digits. Question: write a recursive function to find the sum of the digits of a number. The sum underscore of underscore digits function is a great example of using recursion to solve a problem by breaking it down into smaller parts. The function's purpose is to find the sum of all the digits in a number. For example, if you have the number 1234, the sum of the digits is 1 plus 2 plus 3 plus plus. The function begins by checking a base case, which is if n equals 0. If the number is 0, it returns 0 because there are no digits left to sum, and this stops the recursion. In the recursive case, the function isolates the last digit of the number by using n mod 10, which gets the remainder when dividing by 10, effectively extracting the last digit. Then the function calls itself with the remaining digits of the number, achieved by using divide 10, which divides the number by 10 and discards the last digit. This process continues until the number is reduced to 0, at which point the recursion starts to unwind. For example, when some underscore of underscore digits 1234 is called, the last digit 4 is added to the result of some underscore of underscore digits 123, which continues down until some underscore of underscore digits 1 calls some underscore of digits 0 and hits the base case. As the recursion unwinds, the function adds up all the digits, eventually giving the final sum of 10. This method is efficient for handling such tasks as it reduces the problem step by step, making the overall logic simple and clear. 4. Reverse a string. Question: write a recursive function to reverse a string. The reverse underscore string function is a clear demonstration of recursion being used to reverse a string. The way it works is by repeatedly breaking down the input string into smaller parts and reconstructing it in reverse order. The function begins with a base case which checks if the string is empty. If it is, the function returns the string as is because an empty string or a single character string is already considered reversed. In the recursive case, the function takes the last character of the string using 1 and appends it to the result of calling the function again on the rest of the string, excluding the last character as 1. For example, when reversing the string hello, the function first isolates the last character O and then calls itself to reverse hello. This process continues until the base case is reached where the string becomes empty. As the function begins to unwind the recursion, it combines the characters in reverse order. For instance, H gets added to the result of reversing the rest of the string, which forms A, and so on until the full string is reversed into a line. This approach efficiently breaks the problem down, making it easier to handle each smaller piece of the string and then putting them back together in reverse order. 5. Power of a number. Question: write a recursive function to calculate the power of a number x power of n. The power function demonstrates a recursive approach to calculating the result of raising a number x to the power of n. The function starts by checking a base case which states that any number raised to the power of 0 is 1. So if n is 0, the function returns 1. This provides a stopping point for the recursion and ensures that the function eventually terminates. In the recursive case, the function multiplies x by the result of calling itself with n1, effectively breaking the problem down by reducing the exponent by 1 each time. For example, when you call power 2, 3, the function breaks it into smaller problems. First 2 multiplied by power 2, 2, then 2 multiplied by power 2, 1, and so on until it hits the base case power 2, 0, which returns 1. Once the base case is reached, the recursion unwinds and begins to multiply the results together. For power 2, 1, it returns 2 multiplied by 1 equal to 2. For power 2, 2, it returns 2 multiplied by 2 equal to 4. And finally for power 2, 3, it returns 2 multiplied by 4 equal to 8. This process shows how the function recursively breaks down the problem into smaller parts and then builds the final result step by step. The function efficiently calculates powers of a number without needing a loop, making it a simple and elegant solution. 6. Greatest common divisor GCD. Question: write a recursive function to find the greatest common divisor GCD of two numbers using Euclid's algorithm. The GECT function is a classic example of recursion used to compute the greatest common divisor GCD of two numbers a and b using the Euclidean algorithm. The GCD of two numbers is the largest number that divides both a and b without leaving a remainder. The function starts by checking the base case, which is if b equals 0. In this case, the GCD is simply a, since any number divided by 0 leaves the other number unchanged. This base case also provides a stopping condition for the recursion. In the recursive case, the function uses the property that GCDFB is the same as GCDB, a %b, where % is the modulus operator, which gives the remainder of the division of a by b. This continues until the remainder becomes 0, which triggers the base case. For example, when calling JEC4818, the function calculates the GCD as follows. 1. GCD4818 calls GCD48% 18, which simplifies to GCD18 122. GCD1812 calls GC12 18% 12, which simplifies to GC12 63. GC12 6 calls GCD6 12% 6, which simplifies to GC6 0. Once the remainder is 0, the function hits the base case and returns 6, which is the GCD. As the recursion unwinds, the function returns 6 at each step, confirming that the GCD of 48 and 18 is 6. This recursive approach efficiently breaks down the problem by continually reducing the size of the numbers, eventually leading to the result with minimal computation. 7. Tower of Hanoi. Question: write a recursive function to solve the Tower of Hanoi problem. The tower underscore of underscore Hanoi function is a classic example of recursion used to solve the Tower of Hanoi problem, which involves moving a stack of disks from one peg source to another peg target using an auxiliary peg while following specific rules. The rules are that only one disk can be moved at a time, and a larger disk can never be placed on top of a smaller disk. The function works by breaking down the problem into smaller steps until it reaches the simplest case where only one disk is left to move. The function starts by checking the base case, where if there is only one disk N1, it directly moves that disk from the source peg to the target peg. This is the simplest possible move in the Tower of Hanoi problem. In the recursive case, the function performs three main steps. 1. It moves the top N1 disks from the source peg to the auxiliary peg using the target peg as a temporary holding area. 2. It then moves the largest disk from the source peg to the target peg. 3. Finally, it moves the n-1 disk from the auxiliary peg to the target peg using the source peg as a temporary holding area. For example, when solving for 3 disks, the recursive process first moves 2 disks from peg A to peg B using peg C as an auxiliary. Then it moves the largest disk 3 from peg A to peg C. Finally, it moves the 2 disks from peg B to peg C using peg A as an auxiliary. This recursive breakdown continues for larger values of n, making the Tower of Hanoi problem an excellent demonstration of recursion action. The function efficiently reduces the problem into smaller solvable parts, handling each move step by step until all disks are transferred to the target peg. 8. Check if a string is a palindrome. Question: write a recursive function to check if a given string is a palindrome. This underscore palindrome function is a recursive approach to checking whether a given string is a palindrome, meaning that the string reads the same forward and backward. The function works by comparing the first and last characters of the string. If they are the same, it then recursively checks the substring that excludes the first and last characters. This process continues until it reaches the base case, which occurs when the string has either no characters or only one character left, both of which are considered palindromes by default. In the recursive case, if the first and last characters match, the function calls itself with the substring between those two characters. For example, with the input radar, the function first checks if the first R and last R match, which they do. Then it moves inward to check the substring ADA and so on until the entire string has been validated. However, if the first and last characters don't match, the function immediately returns false, meaning the string is not a palindrome. For instance, with the input hello, the function finds that the first H and last O don't match, so it concludes that hello is not a palindrome without further checks. This function is efficient because it reduces the problem size at each step, checking fewer characters as it progresses. It provides an elegant and straightforward solution to determining whether a string is a palindrome using recursion. That wraps up our practical interview questions on recursion. As you've seen, mastering recursion is all about understanding how to break down problems into smaller parts and having a solid base case. Make sure to practice these examples and explore how recursion can simplify complex problems. If you found this helpful, don't forget to like, share, and subscribe for more interview prep and Python tutorials. Thanks for watching, and I'll see you in the next video.